Finite fields is a math concept you'll need to understand in order to learn the cryptography behind a Bitcoin. In order to understand finite fields, you'll need to know what an element, a set, and a field are. An element is a distinct object that belongs to a set. A set is a collection of elements. An element could be any object, like an integer or a color. A set contains multiple elements. One set could contain 3 integer elements, 1, 2, and 3. Another set could contain 3 color elements, red, green, and blue. Now that you understand sets, you can move on to fields. Fields are sets where addition, subtraction, multiplication, and division are defined. You are probably familiar with the field of all real numbers. This field can be represented as a number line going from negative infinity to positive infinity. You can add, subtract, multiply, and divide one element by another on the line, and it will always be another element on this line. Finite fields are similar to this infinite field of real numbers, except it is a finite set of whole numbers. A finite field is represented by a circle instead of a line. Only whole numbers exist on the circle. The length of the set, or the number of elements in the set, is referred to as the order. The order is represented by the letter P because the order is either a prime or prime power. The fields we will work with will be prime order. The prime number used in Bitcoin's cryptography is rather large. Because it is a field, the mathematical operations of addition, subtraction, multiplication, and division must exist. They will be different from the addition, subtraction, multiplication, and division you are used to, but the same basic behavior you are familiar with still applies. Let's define them. Modular addition is used in finite fields. It is similar to regular addition, except you wrap around the circle like a clock. 11 plus 5 in the finite field of order 13 equals 3. Modular subtraction is similar to modular addition, except you travel counterclockwise around the circle. 3 minus 10 in the finite field of order 13 equals 6. Finite field multiplication is modular addition multiple times. 6 times 3 in the finite field of order 13 equals 5. You can multiply a finite field by a scalar and it will return the same set with elements out of order. This will be important when we learn division. Exponentiation is simply multiplication multiple times. It becomes computationally expensive as exponents become large. 5 to the third power in the finite field of order 13 equals 8. Finite field division is the least intuitive operation. In order to perform it, we must use Fermat's little theorem, which says that for any prime p, any integer a raised to the prime value minus 1 equals 1. This theorem is easy to derive. Recall that a finite field can be multiplied by a scalar, and the result is the same field. We can multiply all elements together and reduce using factorial notation. The factorials on each side cancel out, and we are left with Fermat's theorem. To perform division, multiply by the inverse. Then multiply by Fermat's theorem, the equivalent of multiplying by 1. Add the exponents of like bases and compute the finite field multiplication. 8 divided by 5 in the finite field of order 13 after 30 million rotations around the circle equals 12. In conclusion, finite fields are sets of whole integers where addition, subtraction, multiplication, and division are defined. The order defines the size of the field. Addition and subtraction are similar to adding and subtracting hours on a clock. Multiplication is addition multiple times. Exponentiation is multiplication multiple times. Division is exponentiation to values near the order of the finite field. Division in high-order fields is extremely computationally expensive. To learn more, check out Chapter 1 of Programming Bitcoin on GitHub.